Hello everyone, Mr. Fawcett here with another lesson regarding derivatives. We're going to talk more about the relationships between the original function and its derivative today, and really focus on being able to explain what's going on with one or the other if we're given either the function or the derivative. So this is going to be a two-part lesson. To start off, we're going to look at this chart right here, and they give us characteristics about the derivative. What I need you to do is try to come up with what that is telling us about the original function. So for instance, it says f prime of x is equal to 0. Okay, what does that mean about the original function? What could be occurring there, or what's happening? So pause the video, take some time to fill in the right side of the chart. You do not need to do the graph at the bottom. We actually have something else we're going to do before we start to sketch that graph. So just focus on the chart for now. Okay, so first row says when f prime is equal to 0, f of x is something. So you may say f of x has a relative min or max, and you're basically correct, except that it may not. So it's a possibility it could have a relative min or max. And I know up until now, I think that's pretty much all we've talked about occurring when f prime is equal to 0. But I'll show you in a second that it doesn't always have to have a relative min or max when f prime is equal to 0. But it is a possibility. So f of x can have a relative min or max. And here's why. Let me sketch a couple of examples. Let's say I have a graph of f of x, and it's just a nice little parabola here. Well, we know that this point up here, right, is going to be a relative max. So we need to figure out what's going on with the derivative when we have a relative max. Well, if we pick a point on this side of the relative max, right, we have a tangent line with a positive slope. And on this side of the relative max, we have a tangent line. Oops, let's do one that's a little bit better than that. I want to get rid of the whole thing. Okay, we'll just quickly restart this. Okay, so if I pick a point on this side, it's going to have a positive slope. And if I pick a point on this side, it's going to have a negative slope. So our derivative needs to be going from positive to negative when we have a relative max. And we can see that down here. When f prime changes from positive to negative, f of x has a relative max. Relative maximum. Now, let's see what has to occur when f of x has a relative minimum. And again, sometimes sketching these out helps. So we have a relative minimum down here. And let's see what's going on with our derivative. So on the left of the relative minimum, we're going to have a derivative that has a negative value because our tangent line has a negative slope. And on the other side, we're going to have a positive derivative because our tangent line has a positive slope. So when our derivative changes from negative to positive, we have a relative minimum with f of x. Now you may say, well, what are the other options? Like, is there any other option for when we have a horizontal tangent line? And the answer is yes. Let me draw you an example. So let's say we have a graph here, and let's say I have a graph that looks like this. So a little cubic function here. Now, you know what, I can actually make this look a little bit more like it has a horizontal tangent line. So with this function right here, it's pretty clear that we have a horizontal tangent line at this point, right? The tangent line is going to have a slope of 0. The problem is directly before that horizontal tangent, so directly before, we have a tangent line with a positive slope, and after the horizontal tangent, we also have a tangent line with a positive slope. So in this case, our derivative doesn't change signs. It goes from positive to 0 back to positive. When this happens, we're not going to have a relative minimum or maximum. Okay, but it is a option for when the derivative is equal to 0. So for there to be a relative maximum or a relative minimum, the derivative must change signs. It's got to go from positive to negative or negative to positive. If it doesn't, there's no relative minimum or maximum. And we'll go more into this in later lessons. Let's fill in these other two. So when the derivative is greater than 0, or when it's positive, our original function is increasing. And when our derivative is less than 0, our original function is decreasing. Okay, so there's a little review of the relationships we've talked about in previous videos. We're now going to look at picking out relationships from a graph and then eventually sketching a derivative graph based on what the original function looks like. So let's get rid of this. And we're actually going to go down to the second page. We're going to skip over this part for now and come back to it. And let me make this a bit smaller so we can see almost all the questions. All right. So we have a graph of f of x, and we are asked 6 questions, I believe. Yep, 6 questions about the derivative of f of x. So questions about f prime. Let's start with number 1. It says approximate the value of f prime of 4. So when we see derivative, we should think slope of the tangent line. And we're going to evaluate this derivative at 4, which means we want to find the slope of the tangent line when x is equal to 4. So the easiest way to estimate that, because this is approximate, not find an exact answer, would be to draw the tangent line in at x equals 4. So again, that's not perfect. Yours doesn't have to be. You just want a little sketch. The big thing here is to understand that the tangent line is going to be positive when x is equal to 4. Okay, it's not going to be negative. It's not going to be 0. Whether you tell me it has a slope of 1 or 1.5 or 2 is kind of irrelevant. We're just approximating. You just need to make sure you have a positive slope there. Okay, number 2, at what values of x is f prime of x equal to 0? Justify your answer. So when our derivative is equal to 0, well, think about what the slope of the tangent line should be there, right? The slope of the tangent line should be 0, which means we have a horizontal tangent. So let's look at all the places we could sketch a horizontal tangent line. Well, we could certainly sketch one right here. We could sketch one down here. And we could sketch one up here. Right? So think about what those x values are. Let's write those down. We have x equals -4, x equals +1, and x equals 5. And our justification again is just f of x has horizontal tangents at these x values. All right, let's move on to number 3. And again, hopefully you've paused the video and you already attempted to answer these questions before we went over them. If you haven't done that up to this point, why don't you go ahead and pause it now and see if you can answer the rest without hearing the explanations first. Number 3 asks us, on what open intervals is f prime less than 0? So think about what has to be true for the original function for the derivative to be less than 0, for the derivative to be negative. Well, the original function needs to be decreasing. If the original function's decreasing, the derivative will be negative. So the original function's decreasing from -4 to 1, open interval, and 5 all the way to infinity. So we have open interval -4 to 1, union 5 to infinity. And our justification is because f of x is decreasing over these intervals. That justification is important. It will be something you need to do consistently throughout this course, but we're specifically talking about this unit for now. Number 4, on what open intervals is f prime of x greater than 0? So when is it positive, which means our original function must be increasing? Well, it looks like we have -infinity to -4, and then from 1 to 5. So -infinity to -4, union 1 to 5. And this again is because f of x is increasing over these intervals. And number 5, the last one that we can see on this page at least. At what values of x does the graph of f prime go from being below the x-axis to above the x-axis? If we're going from below to above the x-axis, that means we're going from negative y values to positive y values. So where does f prime go from positive to negative? And we talked about this up above, right? It's in our chart. F prime is going to go from, sorry, I may have said negative to or positive to negative. We are looking from going below the x-axis to above. So we're looking from negative to positive. And that's going to occur when we have a relative min. Our derivative will be negative, and then it will be positive on the other side of that relative min. So let's look and see where this graph has a relative minimum. That occurs at x equals 1. So we'll say at x equals 1 because f of x has a relative minimum here. Okay, and all these questions we're answering are going to help us eventually sketch the graph of f prime. And our last question here is just the opposite of what number 5 was asking. I will clear this so we can quickly read it. Oops. So it says, at what values of x does the graph of f prime go from being above the x-axis to being below the x-axis? So if the derivative is going from, I'm just going to move this up so we can see the graph. If we have an original function that has a relative max, right, then our derivative is going to go from positive tangent line slope to negative, because our tangent line has a negative slope here. So if we want to know where the derivative goes from above the x-axis to below the x-axis, well, we need to look for relative maximums. And we have one here at x equals -4, and we have one here at x equals 5. So our answer to number 6, I'll just put this up here, at x equals -4 and x equals 5, because f of x has relative maximums at these values. Okay, last thing for this video, we are going to go back up and we are going to sketch the graph of what f prime should look like. So again, it's the same original function, f of x, and let's make this a little bigger. And we want to sketch out, again, what the graph of f prime would look like. Now, we've answered a lot of questions about where f prime is negative, where it's positive, where it's equal to 0, etc. So you can use the answers to those questions to help you sketch out the shape of this. So take a minute, then come back and compare your work to mine. Okay, so I think the first thing we should do is show where our graph has horizontal tangents, which means the derivative is going to be equal to 0. So we said it has horizontal tangents at x equals -4, x equals 1, and x equals 5. So we want to put our zeros right at those x values. And that kind of breaks our function up into intervals, and we can just focus on what's going on in between those zeros. Okay, so next thing we can think about is where will our derivative be positive? And we answered that question, we gave the intervals, but our derivative is positive when our original function is increasing. So let me use blue for those intervals. So we had from -infinity to -4, and we had from 1 to 5. So our derivative needs to be positive from -infinity to -4. So we can have it come down like this. And from 1 to 5. Now on the interval 1 to 5, what should our derivative graph look like? Should it be linear? Should it be a parabola? Well, if we look at the interval 1 to 5, let me draw a couple of different tangent lines here. Okay, so we have our two horizontal tangents at 1 and 5, and then we have some other horizontal tangents we can draw. If I could keep this on my pen and not my eraser. Okay, here's a tangent line here. Do one in green. And the last one in purple again. So we can see that the tangent line, if we look at the first purple one, we go from the pink one, which is 0, to a purple one, which is positive, to a green one, which is more positive, but then we have another purple one that's less positive, and then a pink one that's 0. So essentially, we're going to have something that looks like this. It's going to get more positive, and then get less positive as we get towards our other 0. Something that looks like that. And if you didn't keep that as a curve, if you just left that as like a little pointy triangle like this, you still understand the idea. We don't know exactly how steep that curve is, how flat it is. All we know is that the derivative gets more positive, then it gets less positive as we come down to the other 0. Okay, intervals where our derivative is negative. So that's going to be when our original function is decreasing. Let's do this in pink. Well, it's decreasing from negative, still on my eraser. There we go. From -4 to 1, and from 5 to positive infinity. And same rule is going to apply. It gets more negative, then it gets less negative as we go towards the other 0. For this interval right here, from 5 to infinity, the derivative just keeps getting more and more negative because our graph's getting steeper and steeper and steeper. So it looks something like this. So again, we don't know exactly how stretched these portions of the graph should be. Should they go a little bit further up? Should the pink one be stretched a little bit further down? Because we don't know exactly the values of those derivatives. We just know the signs. We know that they're negative versus positive. So key points of what your graph should look like: you should have the zeros labeled properly, and you should have the derivative being positive or negative whenever the original function is increasing or decreasing. Okay, we're going to call it a video. We are at 20 minutes. We will come back for part 2 of this video, and we will look more at some graphs, as well as get into some algebraic forms of functions and answering questions about derivatives and original functions based on the algebraic form rather than a graph form. All right, this has been Mr. Fawcett. As always, enjoy the rest of your day.